Okay, we're going to pick up with moments and we're going to talk about equilibrium. Remember when we talked about equilibrium before? It's when something is either not moving at all or when it's moving at a constant speed. And now we're talking about things that are rotating, either not rotating at all or rotating at a constant speed. And just like we said, the sum of the forces is equal to 0, the sum of the moments will also be equal to 0 if it's in equilibrium and not moving. So a little seesaw, or teeter-totter, whatever you called it when you were a kid, is a perfect example. So for example, if I have two teddy bears sitting here and they weigh the same thing and they're the same distance out, they're going to balance perfectly. But what if we put a bigger one on one side? The bigger one clearly goes down. You all experienced this when you were kids, and there was always the kid that was the lighter weight kid who would always go up and the bigger kid would always go down. In order to balance this out, the bigger kid needs to scoot in a little bit so that he has a shorter distance. And we can represent this with forces. If I know the distance of the lighter weight teddy bear, and I know the weight of the bigger teddy bear, I can figure out how close we need to put this one to get it to balance. I'm just going to call this X. This should also look like levers that we did back at the beginning of the year with simple machines. So here we're going to do sum of the moments. So what I do is I say the moment on this side plus the moment on that side needs to equal 0 for this to balance. So the one on this side is positive and the one on that side is negative. This is the other side, the other way I just remember it. I draw this little thing, actually this one right here, I always draw at the top of my page when I'm working with moments. Counterclockwise is positive. So I just draw this little thing at the top of my page, and that's how I always remember. This direction's positive, that direction's negative. So another way to think about this is I can take this moment and put it on the other side and say when I put this on the other side, M1 has to equal the negative of M2. So my force times distance on this side needs to equal my force times distance on that side. So I can plug those into my equation here. Force times distance on this side minus force times distance on this side equals 0. Do a little math and solve for D. It's an Algebra 1 problem. Notice the units all cancel out, leaving us with this teddy bear needs to be 2.5 feet out. I just want to show you this briefly. Where we're headed with this is we're eventually going to be looking at trusses where we're going to use the sum of the forces and the sum of the moments on a problem like this to calculate all our internal forces here. We're not going to get to that point yet, but we will come back and use this stuff, so this is why this stuff is important for you to know.